Last time I told you a bit about something to do with Riemann surfaces and quadratic functions. There was some things were not quite correct. I should correct, and anyway I should review it. So I will start by reviewing the last bit I did, and I have to apologize. Some of these transparencies get a bit blurred. The black fades after a while; it becomes like invisible ink. And the other colors, well, not too bad. I hope you can read it. I'll remind you what I did last time. So let's start this way. I'll be more simple this time. We have a vector space of even dimension over a field of two elements. And if you suppose you've got non-degenerate bilinear form, then a function is called a quadratic function if it satisfies the identity there, q of x plus y equals qx plus inner product xy plus q of y. In particular, this implies that q of 0 is 0. So before I was dealing with affine spaces, there was no distinguished origin. When you got a vector space, there is a distinguished origin, and the quadratic function is supposed to be 0 at the origin. Then there are just two possibilities for such a quadratic function, basically, and they are distinguished by the number of times the function takes the value 0. So q inverse of 0 is either a number n plus, or it's a number n minus. That should be a minus there. And n plus is bigger than n minus, but the formula is there. One of them is a bit more than half, and the other is a bit less than half. And the one which is a bit more than a half is more than a half because it contains a Lagrangian subspace, a space in which the quadratic function is identically 0. And so it has to have at least half as many points going into 0. So those are the only two possibilities. And the half invariant is defined to be 0 or 1, distinguishing the two cases. And I always have difficulty remembering which is which, but you're supposed to remember it by democratic vote. The half invariant is 0 if 0 is taken more times than the other one. So half invariant is 0 when q to the minus 1 of 0 is n plus. The other one is half invariant 1. Now, you can, as I did before, you can extend the definition of quadratic function to an affine space with the translations being the vector space associated to it. And again, just two possibilities, depending whether the function takes the value 0 n plus times or n minus times. If you have chosen an origin in the affine space, then if the quadratic function is 0 at that point, then you've identified what we had before, and these are the numbers. Okay, so that's a quick reminder of this half invariant story, which is slightly difficult to remember. And then we apply this to the case of a Riemann surface. If you have a Riemann surface of genus G, and then you consider the spin structures on the Riemann surface, every Riemann surface can be made a spin. The condition to have a spin structure is that the certain topological invariant second Stephen-Whitney class is 0. When that's the case, there are many choices, and the choices correspond to the cohomology H1 with mod 2 coefficients. And so you get, and the set of spin structures is an affine space with the corresponding translation space being the cohomology with Z2 coefficients. You can change one spin structure by an element of this group, which gives rise to a line bundle of square 1. And then we define the invariant Q of S. Now you think of the Riemann surface having a complex structure, then you can talk about the space of sections of the line bundle, or zero-dimensional chief cohomology of the Riemann surface with respect to the line bundle, and that, taking modulo 2, is the function of S. We associate fundamental theorem is a topological invariant that doesn't change as you vary the complex structure, and that is mod 2 invariant function defined on the affine space of spin structures, and it's a quadratic function. And then which quadratic function it is a theorem, and the theorem says that it takes the value 0 n minus times, smallest number of times. In the particular case when the genus is 1, then that's an elliptic curve. In that case, the canonical divisor is trivial, so that it actually is a distinguished spin structure corresponding to the trivial line bundle. If you choose that one to be your origin, then H0, that has one section, the constant sections, and it's 0 for all the other three. There are no holomorphic sections for the other three. So in this case, the value 0 is taken 3 times, but that's because we have this particular distinguished element's origin. That's the element whose value is 1. If you want to take an origin value is 0, then it switches around and you get the other value. So the conclusion is that this other way, the half invariant is 1. I'll come back to that later because I'm trying to build up to the next part of the story, but this was just to remind you about the... Now, another way of thinking of Riemann surface spin structures is just think about cobordism. In general, manifolds, you talk about cobordism of two manifolds if they have a boundary, one manifold at one higher dimension, and there are different kinds of cobordism depending what structure you put on the manifold. Spin cobordism means the manifold should be spin. So if you have a spin Riemann surface with a spin structure, then it will be a boundary if the Riemann surface bounds a three-dimensional manifold and also the spin structure extends to the interior. And this number, Q, the quadratic function we've taken, is mod 2 invariant, is a spin cobordism invariant. In other words, it is 0 if and only if the manifold bounds. It's the only spin cobordism invariant. And the theorem we proved before can be restated like this. There are n plus spin structures which bound. So of the curve of genus 1, 3 spin structures bound. They're the non-trivial line bundle. And 1 spin structure, the trivial line bundle, doesn't bound. You'd think it'd be the other way around, but that's the way it is. Now, that finishes off the last lecture. Today's lecture, I'm going to try and tell you a bit about the Kerver invariant and the magic square. And but the point about the example with Riemann surfaces and Kerver, it gives you an introduction to it, you see, and a especially simple case, which has others. So the general Kerver invariant story is this. First of all, I remind you, if you have manifolds in general, you can talk of manifold which is framed. Now, framed manifold, roughly speaking, means that it's parallelized. You can have a framing of the tangent bundle. But it doesn't need to be the tangent bundle. It's what's called a stable framing. It means you can add a trivial bundle to a manifold, and then you frame it then. Or equivalently, you frame the normal bundle when you embed your manifold in a large dimensional sphere. For example, an ordinary sphere, in general, is not parallelizable. But if you add one trivial bundle, then the sphere is in Euclidean space, and then you can identify the sum of the tangent bundle of the one normal direction with the frames in Euclidean space. Those can be trivialized. So the sphere is always stably trivialized that way. Now, the cobordism classes of framed manifolds, as I say, you take a manifold which bounds together with the framing, and you assume the framing extends. That's a very special class of cobordism theory, and those are of interest because they are identical with the stable homotopy groups of spheres. Now, the homotopy groups of spheres are the groups you get by mapping a sphere one dimension into another one. If you take a sphere dimension m plus n, mapping into Sn, where n is large compared with m, then this is independent of n. That's called the stable homotopy. So we just written about like pi ms, stable. These homotopy groups are one of the main problems people started to study in homotopy theory. The problem is still unsolved. A complete classification, complete theory of all the stable homotopy is not yet known. And these are part of this Kerver problem is part of that story. This relationship between homotopy groups of spheres and framed cobordism was really introduced by Pontryagin and developed by René Thom in general cobordism theory. Pontryagin-Thom construction, it's called. So it's a way of trying to use, if you want to understand homotopy groups of spheres, the idea is you use the inverse image of a point. That's the idea. And then that is, if you think of a large sphere mapped onto a small sphere, then the inverse image of a point is a manifold of codimension m, sitting inside a big sphere, and the normal bundle is really just pulled back from the normal bundle down below. You have a point, you take a basis of the normal space, the tangent space there, you just lift it up along the other one and give you framing in the normal direction. That's why these are framed manifolds. So this is the fundamental theorem. Now the Hopf invariant, which we mentioned before, is a particular invariant which maps the stable homotopy to Z2, integers modulo 2, which I described examples of. And the theorem of Adams says Hopf invariant equals 1, that's non-trivial, if and only if M has 1, 3, and 7 dimensions, only three dimensions. And this was known long before, in general, that m had to be a power of 2 minus 1. That's easy to prove. The harder theorem was to prove that it only occurred for 3 values. And that was all proved by Adams, and I gave you last time a sort of short proof by K-theory. And the Hopf vibrations, which I mentioned, the maps of the 3 sphere to the 2 circle, 7 sphere to the 4th sphere, 15 sphere to the 8th sphere, where the fibers are the circle complex numbers of absolute value 1, the 3 sphere quaternions of absolute value 1, S7, the arctonians of norm 1. These give you the 3 basic examples which have Hopf invariant 1. Now, we go on to talk about the covariant variant in the same context. So the covariant variant is, this is very, very faint, I'm sorry. It becomes almost like invisible ink. For some reason, after a while, it becomes secret. But what it's supposed to say, you consider a manifold of dimension 2n minus 2. Okay, that's just the way I've written it. And the middle homology is hn minus 1. So, mod 2 coefficients, and I assume there the cup product of 2 classes, the evaluation, give you the bilinear pairing. Then a framing, now this is an important fact. That's true for any manifold. If the manifold is framed, and you've chosen framing, then that defines the quadratic function, Q, on the cohomology. It's not so easy to define. I'm not going to give you the definition. In fact, it took a long time for people to find the general definition, but let's believe there is a way of defining a quadratic function from a framing. So if you've got a manifold with a framing, it has a quadratic function. And then we consider this quadratic function, and the quadratic function on this cohomology of the vector space has an half invariant, 0 or 1. And the covariant variant of the framed manifold is defined to be the half invariant of the quadratic form. Okay? So we have something which we call the covariant invariant, which is a map of the stable homotopy spheres in this dimension into Z2 by this construction. And now it's known by fairly simple methods that the covariant variant is 1. If it's 1, then n must be a power of 2. Very similarly notice to the Hopf invariant. By the way, the dimension of the manifold is 2n minus 2, okay? So the manifold is dimension 2 less than 2 to the k. And examples of such a manifold for k equals 1, 2, and 3 are given by the squares of the ones for the Hopf invariant, namely S1 times S1, S3 times S3, S7 times S7, manifold of dimension 2, 6, and 14. And now these cases, you've got to choose not only the manifold, but you've got to choose the framing. And the framing, when the manifold is framed, is not unique because you change the framing. And the framing you choose is always the framing coming from the group. See, S1 is a group, S3 is a group, S7 is nearly a group. So because it's a group, you can translate a basis around a point, and you get a parallelism, actual parallelism of the manifold, in particular stable framing. So groups and products of groups have natural group framing. It's not the same as the framing that any sphere has, which is to use the interior, or the normal, to use the framing of the ambient space. There are 2 different framings. And this framing only exists in these dimensions because we know that only these spheres are groups, part of the Hopf invariant problem. So these particular ones have covariant variant 1, 2, and 3. Now, other examples of manifolds with covariant variant have been constructed, and they were constructed when k is equal to 4 and 5, the next 2. Now, the dimensions are 2 less than a power of 2. So after 14, it's 2 less than 16. Next one is 30, which is 2 less than 32. Next one is 62, it's 2 less than 64. And those manifolds have been constructed, quite complicated constructions. I don't even know the constructions. But people have constructed them. Now, very recently, this is last year, Mike Hopkins and his collaborators, whose name I've forgotten for the moment, have proved this big theorem. So this problem has been unsolved for 20 years, just like the Adams problem was unsolved for 20 years, and it's regarded as one of the main problems in homotopy theory. they proved that the covariant event equals 1 implies that k equals one of these values, 1, 2, 3, 4, or 5, where we have examples, and possibly k equals to 6. That's not yet known, but no more. We know it has to be powers of 2 when you add 2, but it stops here. So there are only finitely many that are known to be 5, that is possibly 6. The unknown one is dimension 126, 2 less than 128. So that's this rather striking theorem, which you see has a lot of similarities to the theorem about the Hopf invariant. In fact, it's a bit related to the squaring of the Hopf invariant. You see that the dimensions double, and so on. And that is, but the other examples, for example, are not. For example, if you take S7 cross S7 and go up to the next one, which would be S15 cross S15, that gives you a manifold of dimension 30, but it's not, doesn't have, for no framing, that it have k-variant 1. Now, with these manifolds and framing is not unique. And sometimes the manifold with the same frame can have two different framings, one of which the invariance is 1 and one of which is 0. In fact, Riemann surfaces are of that kind. You see, the very first example, S plus S1, is the elliptic curve. I'll come to that in a moment. So then we know in that case there are 4 choices of framing, one of which has k-variant 1 and the others k-variant 0. So, and that's true for the first 3. But in general, it may not be the case. There may be no framing which has k-variant 1. They all have k-variant 0. Or it might be that in every case where there is one, the k-variant 1, there is one with the k-variant 0, unknown. So this is the state of affairs as it was. Mike Hopkins gave a lecture at my birthday conference when I was 80, a few months ago, and I listened to the lecture, very nice, impressive lecture, but I was very struck by this fact that there are these manifolds of powers of 2 minus 2, finite list of examples, and I said, well, where do these dimensions come from? Where do these examples come from? There must be some meaning to them. And Mike Hopkins didn't know, and nobody knew. But then I thought about it again, and I think I talked with Conan Leung over there at a similar conference in MIT, at Singer's birthday conference, and he gave the same sort of talk. And by this time, we thought, well, there should be some relation with the manifolds that come into the magic square. So that's where the connection to the magic square is. But before that, let's go back to the... This is just what I just said. You can have different framings with k-variant 0 or 1. And the question is now, what is the relationship of the spin structures to the on Riemann surfaces to this story? I said they both use half invariants. Now, in fact, it's a special case. Namely, it's not hard to show that for dimension 2 on a Riemann surface, a spin structure gives a framing and vice versa. Spin structure determines the framing, and framings are essentially the same as spin structure. Little piece of geometry, not too hard to prove. So in this case, in higher dimensions, it wouldn't be true. The spin structure is quite much weaker statement than framing, but in dimension 2, there's nothing else. And moreover, they lead to the same quadratic function, the same coordinate invariant, namely what we got by thinking of this mod 2 index is the same as the k-variant invariant defined by other methods. And the framings are the same, and the example of the elliptic curve is the basic example S1 cross S1, and as I said, there are 4 framings, one of which is not a boundary, and 3 of which are boundaries. So the example of the Riemann surface was a good introduction because it's the first case. Although in that particular case, the quadratic function has this nice interpretation in terms of classical algebraic geometry and was discovered by Riemann long before Kerver. So I thought it'd be good to mention it here because it's an independently interesting question and it gives you a sort of elementary start. Now, here are the questions that naturally arose when I heard this lecture. Again, they've disappeared, so you have to guess what they were. Is there a uniform description of the finite set of manifolds with k-variant invariant 1? We know the first 3 are nice products of spheres. The next 2 have some complicated construction. And the last one may not exist or not, we don't know. And the second question is, what actually happens for this dimension 126? Is it a manifold of k-variant invariant 1 or not? Not known yet. If there was a uniform description, you might find it at the same time as finding all the other ones. But we don't know. So that's an unsolved problem. And challenge. And lastly, is there a simpler proof, using perhaps K-theory, of this theorem of Hopkins, which is analogous somehow to the using K-theory for the theorem of Adams? No? Adams' theorem used complicated cohomology operations, a very long paper. K-theory gave a very short proof. Hopkins' thing is also a very long paper, uses a very complicated machinery. Is it possible that there might be a shorter proof? Well, worth looking at. So now the first observation, this is where sort of something starts, is that the four projective planes, which we talked about before, the real, complex, quaternion, and Cayley planes, they explain the finite set with Hopf invariant 1. Hopf invariants come into the stories. They have a natural generalization to this Freudenthal magic square. I should call it a Freudenthal-Tietz magic square, because both of them really worked on this, which is a 4x4 symmetric matrix of manifolds. So I'm going to write down, show you a picture, 4x4 symmetric matrix of manifolds. We call them Pij, to remind you it had something to do with projective spaces. I'll make the indices R and J run from 0 to 3, as in all good elevator floors. It starts at 0. And the first row will be the classical projective planes. And the dimensions go up by 2 every time you move either across or down. So the dimension is 2 to the I plus j plus 1. So at the left-hand corner, I equals j equals 0, you get dimension 2. That's the real projective plane. And at the bottom corner, when I and j are both 3, you get 2 to the 7th, which I think is 128, which is the last one. So all dimensions which are powers of 2 occur between 2 and 2 to the 7th in this square. So it's a very remarkable fact. There are some beautiful manifolds which have these dimensions, powers of 2, of which the projective planes are just the first row and the first column because it's symmetric. So when I knew the second row of this rather well, as I explained. I'd worked on that one. So it's very tempting to think that these manifolds somehow will explain the finite set which come from the K-invariant problem. After all, a finite set of manifolds, these dimensions, and here's a beautiful set. It seems obvious, they have to be corrected. Right? Why did God make the magic square if he wasn't to help us with this problem? So I feel in my bones that this should be true. But, I mean, how do you prove it? Well, what connection could there be? Don't forget, there's a slight difference between the dimensions. They're not powers of 2, they're 2 less than a power of 2. But at least here, conjecture, again, in invisible ink, would say that can we find examples of manifolds with K-invariant 1 which are codimension 2 submanifolds of these manifolds that should be called Pij. No, sorry, the manifolds are called Mij, codimension 2 in the Pij. Or if they're not submanifolds, perhaps related in some way. I didn't insist on there being submanifolds. I wanted how to be associated with this magic square so that they sort of naturally exist. And if it's uniform, we should work all the way to the end and give us the information about the 126. So that's, you agree that's a reasonable conjecture. I mean, it's a naive conjecture, but unless you make naive conjectures, you never get anywhere. So, now, what are the facts about this magic square? There's a lot of literature about this. This is experts, in which Colonel Young is one. If you have any questions, you ask him. You know about this magic square. It has very beautiful properties. So let me just tell you some of them. First of all, each of the entries of this matrix, each Pij, is embedded in the next one. Both the next one to the right and the next one down. So Ij is embedded both in I plus 1j and in Ij plus 1. Each time is half the dimension. And all these embeddings are compatible. If you go around the square, it's commutative. Secondly, each Pij occurs as one component of an involution on either of the two manifolds that follow it, of twice the dimension. So if either you go to the right where it's twice the dimension, there's an involution there, which I call sigma, which keeps that one, the sub-one fixed, or in the other direction, there's another involution, you might call it tau, which keeps that one fixed. Not the whole fixed point set necessarily, I should emphasize, is one component of the involution. And these make them examples of symmetric spaces. Of course, in this notation, if the indices get bigger than 3, you drop them out. But so in this square, each one appears as a fixed point set of an involution in both the one to the right and the one below. Okay, so it's a very nice property. So we have a lot of nice information about them. So now what is this magic square? Well, being a magician, I wave my hands, I abracadabra, magic wand, and here is the magic square. So, magic square. Now, you think of it carefully. So first of all, we start along the top, and there's our famous real projective plane, complex projective plane, quaternion projective plane, and octonion projective plane. And vertically down the same two is the first column. Second row. Well, first is CP2, then we have the product of CP2s, and then we have famous, fairly familiar homogeneous space of the unitary group, which essentially is complex Grassmannian of two planes in a sixth space. Then there is a homogeneous space of the exceptional group E6. Now, that's interesting because exceptional groups don't turn out very often, and here it's turning up. And then I'll say more about that second row. Then the third row, well, it's by symmetry, the first two elements we already know, and then the third one and the fourth one, the third one is a real Grassmannian of four planes in 12 space. And the last one is a homogeneous space of the exceptional group E7. And finally, the bottom row, the first three we already know, and the last corner is homogeneous space of the exceptional group E8. So it's a very beautiful fact that all the exceptional groups E6, E7, and E8 appear in this diagram, part of the natural story. And actually, if you look more carefully, there are two other exceptional groups, F4 and G2. They actually appear also because F4 is the KV plane is the homogeneous space of F4. So you can write OP2 as F4 over something. And G2, the exceptional group G2, is the group of automorphisms of the octonions. So all the exceptional groups are explained in this one diagram. So that's a very beautiful fact because the exceptional groups are, there are a list of exceptions where you do your classification of Lie groups, but this time I show them all appearing in some uniform way. Well, so the statement about the dimensions, you're good at calculation, you can work out the dimensions, they go up as part of 2. And each of these has there are involutions which have the previous one. For example, from the complicated plane, you take the ordinary coordinates, take complex conjugation. The fixed point set that is obviously the real projective plane. That applies also vertically. There's a similar one from the quaternion projective plane to the complex projective plane. There's a similar kind of conjugation with involution, and so on all the way down. There are more complicated involutions further down. I'll come to one particular one. Well, maybe I'll mention that in a moment. Let me carry on with the table. I'll come back to it. We may want to reproduce this table several times. Now, besides these other projective planes, this is to remind you what are the groups that act on these spaces. So the symmetry groups of these manifolds are, there they are, orthogonal, unitary, symplectic, and F4. F4, by the way, formally plays the role of the 3x3 matrix group over the octonions. Then you get these elements of E6, and the last column you see is E4, E6, E7, E8. So those are the groups that enter into this story. I'll keep these over here. I might need them later. Now, I mentioned that the example of one of the symmetries, involutions, that fixes a space is complex conjugation in the complex projective plane. But the more interesting one is to consider the one further down involving the Grassmannians. If you consider the 12-dimensional real space, which is the same thing as complex 6-dimensional space, if you can fix a complex structure, then multiplication by I, let's go to the -1, acts on, it's a certain rotation, on the 4-dimensional space and induces an involution on the Grassmannian-oriented 4-dimensional spaces. That was one of the spaces in our magic square. Now, the fixed point set of that gives you the spaces invariant under I. Those are the complex subspaces. So they give you a complex subspace, C2, inside C6. Now, this is the Grassmannian of real oriented planes. Now, a complex plane carries a natural orientation. So you embed that into the oriented Grassmannian by using the natural orientation. But you could be perverse. You could decide to give it the wrong orientation, in which case you'll get another component, another copy of the complex Grassmannian inside the real Grassmannian. And so you find that in this involution has two components. Both of them look the same, but they're two different ones. And there are two. In this case, that's an important point which we'll come back to later. And in each case, the involutions that give these symmetries are known, and it's known when there is more than one component, and what the components are. There are lists. So this has all been very much studied. Let me make a comment which Colonel Jung here pointed out in his papers. I don't know if he's the originator of it. That is that the symmetry of the magic square, which says that the rows and columns are the same, actually is somehow seems to be related to the famous mirror symmetry, which has come into mathematics or physics. And mirror symmetry is something which interchanges the role of complex structures and symplectic structures. When you have a background metric, then a complex structure, each determines the other, like in Kähler geometry. But if you deal with non-compact things without a metric, then they will be different. So in the non-compact version, where you write non-compact groups instead of compact groups, you'll find the rows and columns not the same. One looks complex and the other looks symplectic. So in some intriguing way, the symmetry of the magic square is related to mirror symmetry. It's a nice observation. What we do with it, I don't know. But it's a very intriguing remark. And is that your observation or is it somebody else's? Good. Okay, well, I think it's a very beautiful idea. But we should make use of it. So now, so my aim is, I'd like to prove, I set out with the aim of proving some of the conjectures about constructing these examples from the magic square. So, first of all, I had to get familiar with the magic square. What are its topological properties, and where can we find it? Then look for some manifolds. So the first thing is to do some experimental work, calculate some of the topological invariants of the magic square, and then I found various remarkable things. I'll tell you what I found. Not complete yet, but... So the first thing is, if you look at all these spaces, they're all of the form G over H, where homogeneous spaces of various groups of maximal rank. They only have odd cohomology. The exceptional case is the real projective plane. There's rather an exception in most of these. Forget about that one. They have no odd cohomology over Q. That's always true. The real projective plane has odd cohomology on two coefficients. The Euler number of these homogeneous spaces is, because there are no odd ones, it's just all the even Betti numbers. And the Euler number of the homogeneous space is well known to be given by the ratio of the orders of the Weyl groups of the groups. So WG stands for the Weyl group of G, Weyl group of H, and one over the other. So if you know the orders of the Weyl groups, you can work out all the Euler numbers of the magic square. Now, the Weyl groups of E6, E7, E8 are known to have the orders I've described there. The classical groups, the orders are easier to write down. If you do some calculations, you get the Euler numbers of the magic square tabulated here. Now, the top line are the projective planes, and the three complex quaternion and octahonian planes have Betti numbers. The cohomology occurs in just dimensions 0, middle, and top, given by projective lines. So obviously they have three Betti numbers, and the Euler number is 3. The real projective plane is a little bit different. If you work modulo 2, which will give you 3. But if you work over the rationals, because of the non-orientability, it only has cohomology in dimension 0, that's 1. So the Euler number is 1. Well, actually, the Euler number will be 1 in either case because you subtract that's independent of the field, but the cohomology over the rationals is only in dimension 1. Now, the second row, and the third row I want to comment on. The second row I'm going to say more about. The third row contains that number 30. And if your arithmetic is good, you'll realize that 30 is not an odd number. And so the most striking thing about this square is that all the numbers, with the exception of 30, are odd. When I saw all the odd numbers, I thought that's very good. It's not odd numbers. You see, we're trying to get to covariant variance being 1 modulo 2. Something odd numbers are, what we want. And why? So here was this nice, nasty counter example with 30. And I had a long argument about this, and then finally I understood it. And the explanation lies precisely in that observation I made that the involutions that fix on that one have this previous one as a fixed component, but it has two copies. And that will explain why you have to divide that 30 by 2 for certain purposes, get an odd number. I'll see that later on. But anyway, going back to the second row. Now, the second row is a very nice set of manifolds because they actually have a concrete meaning. They are the complexifications of the first row. The first row are real manifolds. The second row are complex manifolds. Not only are they complex manifolds, they are actually complex projective algebraic varieties, which contain the real varieties, and they have an involution with the fixed point set being the previous one. So, and these are nice algebraic varieties which you can describe and say quite a lot about. They actually have a name, algebraic geometry. They're called Severi varieties because they have a number of interesting properties. So, here's what I'm saying. The first row is what we know about. So the second row, called the complexification of the planes, I wrote a paper with some years ago with Jürgen Berndt, who was an expert on symmetric spaces, and we studied this second row, and we've proved some results about that space. I won't give all the details, but from what we proved, you have the following sort of general topological picture emerges. Any one of these planes, these complexified planes, has a projection onto a sphere. In that projection, the inverse image of a generic point is a sphere, is a certain sphere of some dimension. And there are two exceptional points. One of them inverse images the preceding projective plane, the real one. So that's the real subspace. And the other exceptional bit is a codimension 2 manifold in there, which is fibered by complex quadrics of the appropriate dimension over another copy of the real projective plane, the dual, the one that describes lines in that space. So there's a very nice geometry going with that picture. In particular, you can use that decomposition to work out the Euler numbers. So the Euler number of the whole space is the sum of the Euler number of the real part plus the Euler number of the bit of the exceptional piece there. That's fibered, so the Euler number is the product of the Euler number of P, the dual P times the Euler number of the quadric. And you plug in the numbers, you get 3 plus 3 times k, where k is the Euler number of the quadric. The quadric has the same kind of cohomology as complex projective space, and the k is involved is 2, 4, and 8. And so you'll find from that the so you notice that these numbers are all divisible by 3, and they are 3 plus 3 times k, where k is 2, 4, or 8. So that explains where the Euler numbers come from, and the geometry of these spaces is rather nice, and I'll say some more about them later on. And I just mentioned here, the real the case of the Grassmannian with the Euler number is 30. It looks like an anomaly, and it's rectified by the fact that the involution has another component. So now, that's some fact. Now I make some conjectures about the topology of the magic square. And these conjectures are very simple conjectures, which look, again, rather remarkable. I should say at once that I've been working on these conjectures for a while. I can prove them by some quite nice, elegant methods, except the last bottom right-hand corner, it's not finished yet. Hopefully it'll still work. So anyway, the conjectures are quite simple. They say various things are odd. Firstly, every one of these manifolds claim is it has odd self-intersection number in the next one. Any manifold is of half the dimension in another manifold. If you move it a little bit, it meets itself in finitely many points. You count the number of points with signs. That's a self-intersection number. And the statement is this number should be odd. And whether you consider the next horizontal one or the next vertical one, they should both be odd. And that should be true all the way through the magic square. First conjecture. Second conjecture, each time you have a little part of the magic square which has two consecutive ones vertically and horizontally, let's think of the bottom, that picture A, B, C, D. The A would represent one projective plane, the B will go horizontally, will be twice the dimension, C will be twice the dimension, and D will be twice the dimension of that. You'll have 4, which will have dimensions of n, 2n, 4n. Now, B and C have half the dimension of D. So it makes sense to ask what is the intersection number of B and C. Put them in general position. Unfortunately, when they sit there, they're not in general position because they should meet in points, but they meet in A which is dimension n. B and C are dimension 2n. D is dimension 4n. They shouldn't meet in 0 dimensions, but they meet in n dimensions. So they're not in general position. So to work out the intersection number, you'd have to deform them in some way to find the intersection number. And that's a bit cumbersome to do. Fortunately, there's an elegant way to calculate them. This is a formula due to Bott a long time ago, in connection, I think, with his work on Morse theory. And that is the idea that if you have two manifolds which do not meet transversely, but meet in two higher dimensions, but if that transversal is what's called clean, and there aren't singularities around, just like happens here, then there is a simple formula. And here's how you do the formula. So first of all, notice that this applies to any case where the dimensions are such that B plus C add up to D, not just the n 4n situation. So now you look at over A, you look at the various bundles that you've got. You've got the tangent bundle of B restricted to A, tangent bundle of C restricted to A, tangent bundle of D restricted to A, which I'll just denote by T, B, C, C, like that, and the tangent bundle of A itself. Now, B and C both sit inside D, so you have a map of the tangent bundle of B plus the tangent bundle of C to D, and because they're not transversal, these actually, there's a kernel to that map, and the kernel actually is just the tangent bundle of A. Then there will be a co-kernel of that map, which we will call F, and defines F. And the dimension of F is the same as the dimension of A. In the case when they were transversal, A would be a point, F would be 0. So the theorem of Bott's is that the intersection number of B and C is actually the Euler number of this bundle F. F can have a name, it's a sort of the excess bundle, or the bundle that measures the failure to be transversal, or whatever you like. So there's a nice formula in terms of the exceptional Euler class of this bundle F. That I've just written down the dimensions here. So we can use that. So these are the two conjectures I have. I'll tell you in advance that I get a sketch for you how one can prove these by some general methods as far as possible. But we haven't quite finished, and I'm not quite sure about the last ones. Of course, in principle, these are all very explicit spaces. And calculating the cohomology of these spaces, calculating is in principle a computational exercise for experts on Lie groups. So, it's the kind of thing you could do for your PhD thesis, is do all this and calculate it by hand. But it will be cumbersome, and it's nicer to see some elegant proof which is more or less uniform. I'm too old. I got my PhD anyway, so I'd rather give a more elegant proof. So I'm going to tell you about ways of calculating this. I won't go through all the details. We indicate how we do the calculations elegantly. The first observation is the following. The Euler number of a bundle is an invariant of a bundle, but it's not a stable invariant. If you add to a bundle a trivial bundle, then the Euler number gets lost. Not entirely. Its reduction modulo 2 is a stable invariant. That's an example of what are called Stiefel-Whitney classes. Stiefel-Whitney classes are mod 2 classes of bundles, like Chern classes are complex bundles, and they are stable. So that means that you can calculate these. Now, the Stiefel-Whitney class mod is the same as Euler class mod 2. So if all we're interested in is to prove something is odd, we can calculate the Stiefel-Whitney classes. Now, because these things are stable, you can work in the sort of kind of Grothendieck group of adding and subtracting bundles. So F is really can be written formally as TD plus TA minus TB minus TC. That's a virtual bundle. It will have a Stiefel-Whitney class. And the intersection number of B and C is that over A. Now, that's one benefit. Now, if you're now dealing with a case where the bottom two, C and D, are complexifications of ones above, A and B, as happens when you go from the first row to the second row of the magic square, then some nice things happen. Because when you have a manifold and you complexify it, it's pretty obvious that the tangent bundle and the normal bundle are the same, because multiplication by I rotates one into the other. So we see that if you look at A inside C, its normal bundle is the same as the tangent bundle. So the tangent bundle of C restricted to A is twice the tangent bundle. Similarly, the tangent bundle of D is twice the tangent bundle of B. If you plug those in and you do some cancellations, you'll see it gets simplified, and you'll see the total Stiefel-Whitney class of F is just the Stiefel-Whitney class of T of B minus T of A. But A sits inside B, so TB minus TA is just the normal bundle. So the Seaver-Whitney class of F is the same as the Seaver-Whitney class of the normal bundle of A and B. But the top Seaver-Whitney class of this normal bundle is just the self-intersection number modulo 2. So you conclude from all this game that the self-intersection number of B and C is the same as the self-intersection number of A and B modulo 2. So that's how. So we avoided having to do any deformation, a little bit elementary arguments. We've reduced the calculation of those self-intersections to the intersection, the calculation of these two submanifolds into a self-intersection, which was the first conjecture. So we see it making some progress. So if that only applies if you've gone to a complexification, it's only going to work at the moment going from the first row to the second row. Now you need some further theorems. And the further theorems we need are just standard theorems. There is the Lefschetz fixed point theorem. Lefschetz fixed point theorem is probably one of the most famous theorems in topology. It says you have a map of a manifold to itself, then the fixed points, which should be counted, are equal to the Lefschetz number of the map. So if the map maps Y to itself, X is a fixed point set, then the Euler number of X is given by the Lefschetz number of F. Lefschetz number is, you take the alternating sum of the cohomology, and you take the trace of the action of F on each cohomology, and you add it up. That's called the Lefschetz number. If the map is identity, that's the Euler number. So the Lefschetz number of F is equal to the Euler number of X. If X was a finite set of points, it would be just the number of points. That's the case you usually think of. The number of fixed points is given by the Lefschetz number. If this manifold is an involution, then every action of F is of order 2. Its eigenvalues are plus or minus 1. So its trace is just the sum of the eigenvalues, and plus 1 is equal to minus 1 modulo 2. So the Lefschetz number actually is the same modulo 2 as the Euler number. So you conclude that the Euler number of Y and the Euler number of X are congruent modulo 2. They have the same parity. That's another nice fact, which enables us to go from one of the manifolds to another manifold, because these manifolds all sitting inside each other as involution. But notice that if the involution has several components, then X means the sum of all the components. And the Euler number means the sum of all the Euler numbers of all the components. If there's only one component, that's the easy one. If there are other components, you've got to allow for those. And so you need to know about the components. So they're explicitly written out. The Euler number of 1 is the sum of the Euler numbers of all the components of the fixed point set modulo 2. So you need to know what the other components are if you want to do the calculations. And then there's another theorem, which is useful. This is a theorem that I guess it comes out of the index theory, and it's called the G Signature Theorem. And it's a general theorem, but I only apply it in a special case. Suppose you have a manifold Y, this time of dimension 4K. By the way, a manifold of dimension 4K has an interesting invariant called the signature, which is similar to the Euler characteristic, but much deeper. You take the quadratic form Y in dimension 2K, given by intersection theory, and you diagonalize it, and you count the number of plus signs and the number of minus signs, and you subtract, and that's the signature. Signature is an invariant of the cohomology of the middle dimension. So suppose you have an involution now, and that X is a fixed point set of the involution. And the theorem is that you like the Lefschetz number, which is like the Euler number, but using map, you can define the signature of F and Y. That means that you break up the cohomology into its sort of what I call it, the plus part and the minus part of intersection form. Each of these is acted on by F, and you take the trace on one minus the trace on the other. Again, if F is an involution, then the trace is the same as the dimension, and so this will be the same as the Euler characteristic. So, and the theorem says that signature here is equal to the signature, now this time, not of X, but of the self-intersection of X. Again, what you mean by that is that you take if fixed points that you take X, and then you may move it a bit if necessary, so it meets itself transversely, then you take a signature of the self-intersection as a manifold. Now, a special case of this, if x is half the dimension of y, then x squared is points. So the signature of x squared is just the number of points. Just called the x squared self-intersection. If x is less than the dimension of y, then its self-intersection is 0. It doesn't meet itself. So there's something simplifying that. Modulo 2, as I've observed, well, first of all, the dimension of x, if it's half the dimension of y, then from that formula, you'll get that x squared is the Euler number of y modulo 2. So this theorem gives us another relationship between Euler numbers and self-intersections. All of these things can now be used in various cases, and we playing around with that magic square, we'll prove the conjecture in various steps. So that'll get you from the first row to the second row. The third row is different. We haven't talked about the third row yet. Now, the idea is that the third row corresponds to quaternionization of the second row. The second row is the complexification. The third row is the quaternionization. It's not quite clear what it means to quaternionize the manifold, but you can look at the tangent bundles and things like that, write down the sort of properties you get, and particularly the second row are Kähler manifolds, and the third row are what are called quaternion Kähler manifolds. In the second row, the property that makes them a Kähler manifolds is they're homogeneous spaces where the factor on the group of the form G over H, where the group H on the bottom contains a circle as a factor. And that circle corresponds to the complex line bundle and complex structure. In the quaternionic Kähler case, the group on the bottom has SP1, the uniquaternion group, times something else. That gives you a quaternion line bundle. And so it's a similar story, but it's not so simple because the quaternions aren't so commutative. Anyway, in the case when we complexified a manifold, I pointed out the relatively trivial fact that the tangent bundle and the normal bundle are the same, because multiplication by I takes you from what tangent to normal. You might ask naively, is the same thing true when you make this quaternionization? Is it true that the normal bundle is the same as the tangent bundle? The answer is no. Even in the simplest case, when you go from the complex vective plane to the quaternion vective plane, it's not true that the complex vective plane has a tangent bundle which is isomorphic to the normal bundle. Even the characteristic classes are different. But it turns out, this is a nice fact, that although they're actually different, modulo 2, the Seaver-Whitney classes are the same. And the Seaver-Whitney classes are what we need to calculate self-intersection numbers. So you can forget about the answer no. As far as we're concerned, it behaves as though the answer is yes. So this enables you to do all this. You can go onto the third row. And using all these various theorems together, we get most of conjectures 1 and 2, leaving a few awkward cases in the bottom right-hand corner, where the last one, of course, in a sense, the last one is the one we're mostly interested in. That leads to the one manifold of 128 dimensions, which is unknown. But anyway, this gets you quite a long way, and the conjecture might be false at the bottom. There might be an exception. Maybe that last one is different. Or you might believe it's all uniform. They should be the same. I would prefer to think they're all the same. So I believe the conjectures should be true. But if somebody after the lecture comes up and says, I've done the calculation while you're talking and it's wrong, I'll thank them. Always glad to have help. Anyway, that was meant to be a quick sketch of how one can go about proving these properties of the magic square. And this rather remarkable property that everything you seem to do comes out to be odd. That's encouraging, since we want to prove something is odd at the end. So, I mean, so far we don't know how to go about it, constructing the manifold, which is a candidate. I've got some ideas which turn out to be wrong, so I've got to go think of some better ideas. But we have a lot of information about the manifolds that appear, which hopefully can be used. Now, next, more questions. This is now getting more speculative. Now, so far, the speculation questions I've asked are, I'm hopeful the answers are yes. But now I've got some more doubtful questions. So the first question is there an analytic definition of the Kerr-Varian variant? The definition given by Kerr-Varian is a very topological definition, homotopy theory, homology theory. But we saw that in dimension 2, there was this definition by index theory. Well, is there a similar one for the covariant bed? At first sight, you think obviously not, because it has the wrong dimension, the thing's not right, and so on. But then, while preparing this lecture, thinking about it at night, not sleeping, and so on, I began to get encouraged. Maybe there is something you can do. Well, let me just tell you the idea I have, which is maybe nonsense. These manifolds are framed, see? If you take an ordinary manifold, then the Dirac operator has lots of nice properties, lots of indices, they give you information about related to characteristic classes like Pontryagin numbers. But when a manifold is framed, all those numbers are zero. So you can't get anything like that. On the other hand, we have some information. If a manifold is framed, suppose it really was framed, not just safely framed, you'd have lots of independent vector fields. Now you can we know that you can use these vector fields to act by sort of Clifford multiplication on things like Clifford algebras and spinors and vector. So we can use these to give us additional algebraic structure to the bundles we normally have. The bundle we normally have with some minimal structure, they can be complex or real. But if you have a lot of vector fields, they have a lot more structure. They'll have extra algebras acting on them. And that means that the Dirac operators you introduce will have extra structures, and they may now have indices in this newer category. And that I know examples where that sort of thing happens. So this sort of thing has been used. So not entirely crazy, but using the framing, we may be able to get an analytical definition. It's a question. It won't take too long to explore. There are techniques for dealing with these manifolds of this kind. Secondly, this is the second part. In the case of the Riemann surfaces, the line bundles acted on the framings by multiplying by line bundles order 2, and that was the vector space on which the quadratic function was defined. Now, in this case, the way you change framings is by mapping into the orthogonal group. If you map your manifold into the orthogonal group, then you can change the framing by that orthogonal group element. And you don't only need the stable orthogonal group, we're only talking about stable framings. Now, the map into the stable orthogonal group is part of K-theory. It's a K-theory of the manifold with an index such as that. Now, in the case of the Riemann surfaces, we took the line bundles, but actually, I should have emphasized, you should take the line bundles and subtract 1 to make them what are called reduced. Then you get something square. That's why you get a quadratic function if you're on a manifold of dimension 2. So to get a quadratic function here, you take things which are what's called filtration in things which are trivial up to the middle dimension, trivial on the lower dimensional skeleton of the manifold, start in the middle dimension and go up higher. And if you multiply two of these elements together, you get into the top dimension and you'll get a bilinear form. And so, this is where you expect to see a quadratic form. So this is the right thing that should replace the line bundles. Whether it works or not, it remains to be seen. And whether what you get corresponds to the K-vary definition also remains to be seen. But this is the kind of thing one would have to do. Now, I'll put in a remark here that this fits with the magic square philosophy in an interesting way. Because I said the magic square, first of all, you have the planes corresponding to the division algebras, and then actually the columns, well, in some sense, you get taking the division algebras twice. You take the tensor product, 2 copies of the division algebra, you get a more complicated animal, and the matrix corresponds to the two sides. And that's more or less what I'm doing here, because I have on one hand the Dirac operator, which uses some of the Clifford algebra, and I'm going to use it again on the vector field. So I think I'm using the same sort of story. Well, be as it may. And last observation I want to make, I'm running out of time, but is this beautiful theorem of Zach, which I can't resist mentioning. Zach was a Russian algebraic geometer who proved a very nice theorem about the second row of this magic square, which I remind you are algebraic varieties, predictive algebraic varieties. And the very first one of these is a famous example called the Veronese surface. It's the embedding of the complex vector plane into 5 space given by quadratics. And it's a degree 4 surface in CP5, and it has the remarkable property that if you take the chords of this surface, take 2 points and join them by a line, well, you're in dimension 4, so each point has 2 parameters, the line has a 5th parameter, you'd expect the chords to fill out the space. But no, the chords don't fill out the space, they all lie on a hypersurface. So And that turned out to be true for all the manifolds in the second row. And then Severi proved a theorem about the Veronese surface that says that this is the only surface with this property. And Zach proved the theorem that all the ones in the second row have the same property, but in higher dimensions. And this phenomenon only occurs in the dimensions 2, 4, 8, or 16. Very remarkable theorem, again showing the uniqueness of things occurring in these powers of 2 dimension, but now in a quite different sounding problem about algebraic geometry. And I've always been intrigued. Does this have any relationship to the proof of the Adams conjecture by K-theory? Would it have any relationship to the proof of this theorem? But it's all very remarkable that the particular dimensions, 2, 4, and 8, 16, turn up in several different contexts: algebraic geometry, topology, group theory, and we were trying to see how they're related. So I thought I couldn't help mentioning that because it's a very beautiful result. And now I've got somewhere here some references, rather inadequate references, but here are references for you. My paper on Riemann surfaces where all the stuff about the square roots comes in is in the Annales Scientifiques Ordinairement Supérieur, 1971. It's in English, fortunately, although it's in a French journal. My paper with Burnt is Breaking Planes, Severi Varieties and Spheres, and it's in some journal, a reference I haven't got with me, but it's the date is 2002, I think. What? Journal of Differential Geometry. Thank you. Then the paper, classical paper by Freudenthal, 1964, about where the magic square probably made its first appearance, and the paper by Zach about the Severi varieties down there. Of course, each of these contains more references. You can follow up and get vast literature. But anyway, sorry to have gone a bit over time, but I hope I've proved no theorems. All I've done is to make conjectures, ideas, speculations. But that's the way mathematics works. You don't have theorems until a long time later, if at all. So maybe next year I'll come and tell you it was all nonsense. Or I'll come and tell you, or perhaps somebody here writes to me and say, here is the proof of the theorem. That's better still. So I challenge problem. Anybody who helps me solve this problem will become famous. Okay? Okay? Yeah.
So, what if you have an analytic definition? What will you find?
Well, if I have an analytic definition, then it essentially means it can be really defined and formulated in terms of K-theory. And once it's in K-theory formulation, it would be like that. And the way in the Riemann surface case, using the analytical definition and formulated in terms of K-theory, I was able to prove the results in question, the quadratic formula, what it was, and so on and so forth. So here, if I have a K-theory definition, then I hope to be able to prove various things about it and possibly prove the theorem of non-existence, because the K-theory was the way we proved the Adams theorem. So if I want to prove Hopkins' results by K-theory, I have to formulate K-theory. That means giving an analytical definition of the invariant. So that's the starting point. If you can do that, then you're at least possibility of getting another proof. So there'll be substantial benefit. But there are lots of questions on the way. Maybe it's not possible. Maybe this is too naive. But at least it's worth investigation. I don't think anybody's tried this particular line, so it's worth trying. Meanwhile, try to find examples the most concrete question is to try to find interesting codimension 2 manifolds in these spaces which could be candidates. I tried one. I thought it was promising. It's obviously wrong. I got an email this morning from Jürgen Baird. He suggests another manifold. It looks nice. Maybe that will work. So, anybody have a good... It should be a natural definition. A definition of manifold codimension 2, uniform in all cases, where it shouldn't be too hard to calculate, and, we should be able to prove it has K very, very 1 easily. That would be the aim. For example, my first example, the key property is that the middle cohomology should be something with a symplectic form when you get a quadratic function, and the simplest case is the middle cohomology is Chevreul rank 2. In other words, behaves like the elliptic curve, or like the other ones. Then it's a very simple exercise when you have just 1 and 3 for your quadratic function. So that's the kind of thing one might hope to find.